because I had to get things. I was just late getting my stuff together this morning. Also, I know I haven't put a new episode up for a while. Of anything, life stuff like that. I'm busy. I got this program going on. But I do want to try and get a new episode of something out soon because, gotta keep that algorithm velocity up. So, I guess we'll go back to talking about representations of SL2, unless there are other questions. Yeah, I didn't do any of my homework in terms of thinking of a good explanation for why schemes I do think one thing that could be argued is the use of the generic point in schemes, and being able to make rigorous the idea of things being generically true. Good morning, Deadstar. First in chat. Saying that something's true on an open-dent subset. Like maybe this was one of the... Because I also know, it's not clear to me why scheme specifically resolves this. You couldn't just do it with varieties. But, the story is that the Italian school was too loose and non-rigorous. And the modern perspective on algebraic geometry allowed us to be more rigorous. But, arguably you could just talk about things on the level of varieties and not full arbitrary schemes. But, I think it's pretty natural once you realize what's going on with varieties and the relationship between ideals and points. It's pretty natural. It's not a very large step away to just say, well, let's just deal with the case of an arbitrary ring. I want to solve polynomials over an arbitrary ring, commutative ring anyways. So I don't know, but I'm just babbling. Like I said, there's probably better expositions out there of why. Okay, so let's go back. I don't think I ever finished this computation over here, where we wanted to... maybe I'll just reproduce it further down. So I've been thinking all these notes as these one-note notes grow bigger. Like, I wonder if it'd be like a cool poster or something. Just a mix of random math. Wonder if I should print them off and make posters or something like that. Okay. So, what did we have? We had, SL2. We had this basis. And we found, first we looked at the natural representation, and we found that could be split. Hello, Femno. Well, good thing you're back, because we're talking about the thing you wanted to talk about, representations of SL2C. We found that could be split into these two eigenspaces, and we described how everything acted there. And then we started looking towards, we considered another representation. By the way, I should mention that this representation is irreducible. Yeah. It's not too hard to see, I mean, it's a two-dimensional representation, so the only way you could have a non-trivial invariant subspace is to have a one-dimensional subspace. So you would need, some vector of the form xy, such that as you act by E, F, and H, it just performs scalar multiplication. And so, I would encourage you just do this on your own. Like, go through each one of the computations and see that you can't possibly have such a non-zero vector. So that representation is irreducible. Okay. Now let's go over to this other representation, which was SL2 acting on itself. So SL2 acting on SL2, where an element X would get sent to the linear transformation bracket X. And we found that there are 3 eigenspaces. And so, of course, they've got to be one-dimensional. 3 eigenspaces of H. And so, again, H just acts on each one of these. We want to figure out what E and F do. But we're going to try and do this we did one of these computations, but I'm going to try and do this in a more general way. So, suppose we had V in V minus 2, or rather, let's get really general now. Suppose we have some representation, V, and I don't know, call it pi or something, and let's decompose V into a sum of eigenvalues, into a sum of eigenspaces of H, right? And now suppose that V is in the alpha eigenspace of H. Then let's see what happens when we apply E. So let's go, I guess I'll call it pi. Let's apply pi E to some vector V. And, well, it could, I mean, who knows, right? It doesn't, it could, in general, you should expect it to be spread out amongst eigenspaces. But in the previous cases, we've seen examples where it actually ends up concentrated in one. And by the way, I mean, kind of has something to do with the fact that there's some sort of eigen relation between EF and H themselves. So so pi E acting on V. And then, so we can test to see if it's in an eigenspace or how it might split up by acting on it by H, right? And so, like, if this becomes a scalar multiple of itself or something, then we know it's in H. Well, we can do, the mathematician's favorite trick, which is doing nothing but looking like you're doing something. By which I mean, we add 0, right? So this would be the same as if we wrote here now minus E minus H plus pi E pi, let's zoom out a little, pi E pi H all times V, right? Are you guys with me? I had this one prof for differential equations in my undergrad. He had so many funny catchphrases. But one of them, he's like, I know. I'll get you guys in the midterm. I know you don't want to study. Are you guys with me? He would always say that constantly. Funny guy. Terrifying when you're in your first year because he yelled a lot. But then, by the time you're in your second or third year, you're like, oh, he's just a teddy bear. Anyways, what is this? This is nothing but the Lie bracket of pi e and pi h, right? This is just the Lie bracket of pi e and pi h and pi e in the Lie algebra GL of SL2, right? The Lie algebra of SL2 as a vector space. But pi is supposed to be a Lie algebra homomorphism, right? So this whole term here is just going to be the same as pi of the Lie bracket of h and e, where now this is the Lie bracket happening in SL2. I'm going to distribute the vector into this pair of terms here and into this term here. So what do we find? We find that we have pi e pi h times v. And this is going to be equal to, well, now we know that this is pi of 2e. Oh, I forgot to write my v here. Hello, Duck with a Monocle. Got distracted by a Forged in Fire video. Forged in Fire. Is that a video game? I'm out of touch with the youth. I don't know what Forged in Fire is. But it's a badass name, so you're forgiven for getting distracted by it. I probably would too. But now, right, V, remember we supposed that V was in the alpha eigenspace of H, and so this is just going to be pi E alpha V. And so, of course, this is linear, so if we pull this 2 out in front and then pull out the pi E's, we get that this is, this whole thing rather becomes alpha plus 2 times pi e v. And so, in fact, it does turn out that this vector, pi e v, is an eigenvector for H, and in fact, it's the alpha plus 2 eigenvector. Just going to lurk. Hell yeah. Hope your messages didn't break my train of thought. My train of thought is impeccable. It cannot be derailed. Oh, shiny thing over there. Okay. Also, unfortunately, I'm streaming from the office today, so I can't do my little song. I've been meaning to, like, I don't have the money to buy myself a nicer acoustic, but been meaning to, like, buy a nicer acoustic for home, and then put my junkier one here in the office, or something. Maybe buy a mini keyboard. I don't know. But here's the point. You could imagine doing this exact same computation, but just with pi f, and probably you should expect by the exact same yoga that it would send an alpha eigenvector to an alpha minus 2 eigenvector. So we have the following picture. We've got v alpha plus 2, v alpha plus 4, and so on and so forth, v alpha minus 2, v alpha minus 4, and here's how H is acting, here's how E is going to act, always list it by 2, here's how H is going to act, or F, and so on and so forth. So we got this pretty little diagram of the representations of SL2. Now, the thing is, though, we could have, so that was just if I started with some eigenvalue alpha. We know that the E and F will just translate between the different eigenspaces. But, you could imagine that I have some, like what if I had some other eigenvalue beta that didn't belong to this string, right? Like, what if beta was alpha plus 1/2, or alpha plus 1 even, right? Or, could be something even weirder, just anything that is not an integer multiple of 2 added to alpha. Well, then notice that if this was also a eigenspace of my representation, right? I sort of draw this diagram. You can see that these two chains sort of don't interact with each other. So actually, I would have this would have to be a sub-representation, right? This would have to be a proper sub-representation, and in fact, I could write this. Maybe this is homework if you understand any of this. Is to convince yourself that this would in fact have to be a direct sum of these two representations, right? So hey, that's not a problem. That's fine. We like big representations too, but that means that since it's just going to be a direct sum as these individual cases, we may as well focus on the case where it's just one of these unbroken strings, right? So, another way to say it is maybe let's try and hone in on which of those representations are irreducible, if possible. Can we classify those? So going back to this picture, though, then I would challenge you to convince yourself that this representation, right, that is SL2 acting on itself, convince yourself that this representation is in fact irreducible. Again, shouldn't be too hard, right? If you have, if it's not irreducible, then there's either a one-dimensional subspace or a two-dimensional subspace. Actually, in fact, the representations of SL2 should be direct sums, but technically you don't know that yet with respect to this conversation. So you should treat those as separate possibilities. However, you could what am I trying to say? I don't know. Brain's too dead. Coffee isn't hitting yet. However, in theory, you could just reduce it to the case of proving there isn't an invariant one-dimensional subspace. Yeah. Okay. So moving along then. In this general theory, right? Let's we'll try and find all of the. So we might wonder then, right? That was irreducible. The first case is irreducible. We know that if we do want to cook up an irreducible representation, we can just restrict. It's necessary to restrict to just one chain of eigenvalues, those which all differ by an even integer with each successive eigenspace. But is this can we pick, for example, any alpha? So can we find for any alpha, can we cook up a representation that has a V alpha eigenspace? And are these representations always irreducible? That's the next question. So we know if we start at some arbitrary alpha, right, we know that eventually applying these successive operations, if we're restricting ourselves to the finite dimensional case, which we should do for now, eventually we'll hit on some alpha n, and where beyond that we just get 0, right? And likewise, we should also, hello Arcturus. Likewise, eventually we'll get down to some alpha. I guess I could write it as alpha minus m, right? Since we know that these are negative, so we could say that this is the smallest, the largest amount I can subtract before I hit 0. And now here's about the point where my memory stalls out, and I forget how to do the rest of the proof, because there's two things that we ultimately want to end up showing. One is that actually alpha is an integer, and two is that n will be equal to m. So it will always be symmetric. So it'll essentially be one of these two cases. Either we have a 0 eigenvalue, as in this case, or going back to our, or where did I put the picture of the original case? Or like in this case, we just have an eigenvalue. Right, we have 2. So depending whether we hit the even integers or the odd integers, essentially, we'll either have a situation like this or a situation like this. So why is that true? Why is that true? I don't remember the reason for that being true. I think we could cook up some formula. I think the way to do it is you suppose you have an eigenvector in the alpha plus n eigenspace. Mind you, sorry, I should not have said that m is equal to n. That is not necessarily true, because that depends on which alpha we chose to start with. So yeah, sorry. As stated, that's not true. But the point is, it still will be symmetric about 0. So either with 0 not appearing if they're odd numbers, or with it appearing if they're even numbers. Well, let's pull up our friends Fulton and Harris. Let's give them a call. Do I not have it? No, I know I have a PDF of it. Representation. No, I have way too many things called representation theory. If I just try Harris? What's the name of their book? Introduction to Representation Theory. Man. The problem when you're a representation theorist and you have way too many no, okay. I don't know where my Fulton Harris is in my computer. Am I just gonna have to prove this on my own? Quite possibly. I don't want to think right now. Perhaps if we jump to the general theory, actually, it might be slightly easier if we do the general theory. Representation theory of first course. Thank you, Eric. Maybe that'll work. I'm pretty sure I don't have it by its full name though, which is it's a practice that I do these days. But you know, a million years ago when I first downloaded it, I did not live by that code. So I'm pretty sure it's just called like Fulton. My search isn't bringing it up right now. Yeah, maybe if we just play around. I mean, I don't want to waste your time, but probably if we just play around with some of these equations, we'll be able to figure it out, right? It's like suppose V is in the largest eigenspace. So what do we know? We know that EV, instead of writing the representation, I'm just going to write it as the action by the matrices. So we know that EV is the zero vector. We know that FV, we know that H of FV is going to be alpha plus n minus 2 times V. And what else do we know? Yo, Lico. How's it hanging? And what else do we know? I suppose we could try applying... we could do F and then E, right? EF V, which would be... Yes, I read your most recent email where you said a bunch of... you called me a moron and an idiot. I can assess someone by their knowledge. Well, I'm not assessing you as a person by your knowledge of proof. But the point was to assess your abilities of proof. And how does one understand the material that they claim? How does one assess if someone really understands the material that they claim to understand? Well, a pretty good way to do that in mathematics is to assess their proof writing abilities on that topic. So we have EF. Again, we'll use the same trick we did before. So we can do EF minus FE plus FE. Then this turns out to just be the bracket of E and F, so distributing E and F on V plus FE V. So we know that this is just HV plus FE V. And H, we assumed that V is in the alpha plus n eigenspace. You have a lot of good creative power and you're over-exaggerating. Sure, yeah, I agree. You definitely creative. Right, I know that was the point of your document, to demonstrate the claim you're writing. But it didn't work. Your demonstration failed. It demonstrated that you have a lot of work to do in terms of formal proof writing. So definitely, you got points for creativity, 100%. We'll give that to you. However, if you want to seriously produce mathematics and connect with other mathematicians and have your work believed and understood, you need to learn how to speak the language of other mathematicians and how to write proofs properly. And I think it would be great if you did learn to do that. But if you're going to do that, you're going to need to check your ego and to accept that you do have more to learn. So I hope that you are able to do that and to continue on your journey of mathematics. But you do have a lot more to learn, especially, if you go around making these claims about how you know all of these fancy things and then you can't back up those claims, mathematicians are going to just think you're a crackpot, and you probably don't want that to happen to you, right? You probably want to be a legitimate mathematician. You have good formal proof understanding, but you've done nothing to demonstrate that. Or create your own journal and publish the claim. Yeah. Well, don't. I mean, the situation with Machizuki's more delicate and interesting than that. But so let's see. Have I gotten anywhere actually with what I just wrote down? I don't know if I actually improved anything. Probably should go look at Fulton Harris, in fact. Let's take a look. Open new tab. Fulton Harris. Yeah, your pod is of genus 0. Yeah, exactly. Lecture 3. Why does this jump to lecture 3? Oh, because maybe I was here before. Okay. Where do we want? Let's go fun section. You'll make sure to send a last email or so proving a simple statement, so you're just reminding me, okay? You're going to relearn induction, contradiction, currying, etc. Okay. Well, that would be great. That would be great if you can give a nice formal proof according to the standard of most mathematicians of a simple statement like that. That would help support the claim that you actually do understand what you're doing, and that would be wonderful. I would love to see it. Let's see. Irreducible representation 146. Nice, I got pretty close there. Just opened it to the book as well. Nice. Let's see. How does that proof go? Yep. We got our diagonalizable. Well, I think we're already going into even greater generality here. Oh no, we're talking about SL2. That's good. Yeah, here's our little trick that we found. Moves the eigenspaces by 2. As immediate consequence of this and the irreducibility of V, all complex numbers must be congruent to one another mod 2. Right, which is exactly where we were. Must form an unbroken string of numbers. Yeah. We'll use the n to denote the last element in the sequence. At this point, we just know n is a complex number, but soon we'll see it as an integer. Right, I guess, this is the claim that these vectors span. So I suppose we need to prove this first. So I suppose this proof isn't. I mean, he uses y, x, y, and h, but I suppose this proof isn't too hard to show. Maybe I'll leave this part to you. What's the prerequisite for Lie algebras? Just knowing basic group theory fields sufficient? Yeah, I mean, you could even really, depending on, of course, like some books will make this more possible than others, but you don't even really, like, with basic Lie algebras, like Lie algebras just over real and complex numbers, you just need, like, basic linear algebra. That's pretty much it, honestly. Like, everything we've done so far in the last couple live streams is just linear algebra, right? We took matrices, we looked at some eigenspaces. That's about it. I mean, okay, if you want to do the general theory, yeah, you don't even need groups, to be honest. I mean, the study of like Lie groups or algebraic groups makes for a good motivation for the study of Lie algebras. But yeah, honestly, you don't even need that much to get into it. Of course, once things start to get more sophisticated, yeah, you'll want some fancier tools. But I mean, this much should be clear, right? We basically just use, so this y is what our f is. We're just using powers of f. So we choose some arbitrary thing in here. And I guess one of the other things though is that we need that this spans the whole space. And so if we knew that these things were all one-dimensional, that would certainly be helpful. One claim that representation theory one might claim that representation theory is linear algebra 3. Yeah, kind of. I mean, once you get done with finite groups, then you got to do some like pretty serious topology. Unless you go in p-adic world, then the topology is like basically trivial. Yeah. So we get x acting by the sequence. Verify this formula by induction. Oh, we get that the one-dimensional spaces, the eigenspaces are one-dimensional as a corollary of this. I see. Interesting. Right. One more time, we use a finite dimensionality. Tells us there's a lower bound. I see. Wait, what is it? I see. And then here, it comes out of this formula. I see. Once it comes out of this formula, and then we assume that we have a smallest power annihilating V. I see. Then we get this formula from it. Mathematics is linear algebra. That's almost true. The mathematics we know how to do is linear algebra, and the problems that are hard are ones that we have not yet reduced to linear algebra. Reminds you of something a professor once said to you about Jordan normal form and something about quiver representations, but you can't remember. You should go back and pay closer attention to that. Actually, not that I know something about Jordan normal form and quiver representations, but this is something that I would actually, Jordan normal form, this is something you should, it's a very important thing to know well, these basic things by linear algebra. I mean, I didn't learn it properly when I first learned it. I was slacking off and stuff, and then it comes up again all the time. Yeah, so definitely worth knowing. Okay, it's 8:51. I kind of want to yap a little bit about like where this is going, the general theme of all of this, where we go next for Lie algebras. But I have a long day ahead of me that starts in like 9 minutes. So yeah, I might have to call it there. So thanks everyone for joining me. Now you know a little bit more about Lie algebras, so you can go prove theorems about that. So go on, get out of here. Go prove some theorems about Lie algebras.